Mic test check, mic test check. Good afternoon, everyone. Given yesterday's issue with the audio, I'm just going to do a test for a minute. I'm going to keep talking at you, and you can let me know if there are any problems with the audio, such as echo, or if I'm cutting out. Let's test. Mr. and Mrs. Dursley of number 4 Privet Drive were proud to say they were perfectly normal, thank you very much. They were the last people you'd expect to be involved in anything strange or mysterious, because they just didn't hold with such nonsense. Mr. Dursley was the director of a firm called Grunnings, which made drills. He was a big, beefy man with hardly any neck, although he did have a very large moustache. Mrs. Dursley was thin and blonde and had nearly twice the usual amount of neck, which came in very useful as she spent so much of her time craning over garden fences spying on neighbours. Did that come through all right? Was it hiccuping at all? No echo? We're all good? Someone write in chat. Wonderful. Chapter 1, The Boy Who Lived. Good afternoon, everyone. It seems we have a few fewer people tuning into the live stream today, and I hope that's because you've started sinking your teeth into the assignment. Again, I know it can be a little intimidating, but we're here for you, and I promise you each and every one of you is capable of at least getting some points on it and doing a good job of it. The mid-semester test results are now also out, and you might have noticed that many of you did a lot better than you were expecting, which should have been a pleasant surprise. Yes, we were a little bit lenient with the grading, but many of you accomplished much more than you initially thought you had. And so that should be a wonderful, pleasing surprise. Because it was quite so difficult, we also did add an extra point to all of you who did put in a real effort and got at least half a point on the test, and also make you feel a little bit better. With the assignment well, we'll gauge the difficulty and see how all of you are doing, and we'll grade it appropriately. So don't get too worried, just put in your best effort. With that, let's get back to our material. Oh, I've gone a little laggy, as happens sometimes. So let's bring up the slides. I can't ever seem to do a live stream without a little bit of lag. Okay, here we go. Yesterday, you'll remember, we were looking at binary search, which is this algorithm to find an item in a list without having to go through every single individual item checking. The basic strategy that we had was go to the middle of the list, or to the middle of our book when we were doing it in person, and figure out whether the thing we're looking for is in the left side or the right side. This only works when the list is already sorted, so you know if the thing that you're looking for is in the latter half or in the earlier half. Let's do one more live demonstration to make that a little clearer. So here I have the book I was just reading from, Harry Potter. And now imagine that I am looking for page 32, and this book is pretty big, so I don't know where page 32 is. One way to find it would be to open halfway, and I see I am on page 70. Well, I know that the pages are in order from 1 to 223. So if I've turned at page 70 and I want to go back, maybe I'll go halfway and I'll go to page 35. I'll open it up, and then I see that I'm still not quite there yet. I'm looking for page 32, and I know it's in the left half of the book, so I'll divide that in half again. And divide in half again, and keep repeating this strategy until eventually I get to the page I'm looking for. And I can do that in far fewer steps than individually turning the pages one by one, which is what I'd have to do if the pages were all out of order and I was looking for the page with the right number. We also started doing our analysis of this algorithm. For our analysis, we needed to figure out how many times we'd go through this halving procedure. So if I half, and then half again, and half again, and half again, how soon will it be until I can't do halving anymore and I've found the item? How many times can you halve something before getting to 1? Well, let's call that number k times, k terms. And we can say that because we know the final answer is 1, n on 2 to the k must be equal to 1. If you then solve that, log n equals k. So we know that there are big O of log n operations that are needed in order to complete binary search. But what we hadn't quite gotten up to yet was actually proving that this process works in a mathematically formal way. This is what we're going to get up to now. As we did with linear search, the trick here is going to be to use an invariant. This is again something that's going to be true at every stage of the program that we use in order to develop our proof. The invariant that we'll use for binary search is as follows. N is bigger than or equal to high, which is bigger than or equal to low, which is bigger than or equal to 0. And x isn't in the half where things are low, in the low half, and x isn't in the high half, where we'll set low and high appropriately. The translation of this is going to be, as I have on the slide, and I'll read it out this once. We are still in the array, so low and high are within the array. Low is smaller than high, which is really important because we're going to want to have these two distinct sections. And the item is not in the lower section or the upper section. And we're going to adjust which is the lower section and which is the upper section appropriately. here is the start of the description of our algorithm, the initialization step. So set low to be 0 at the far left-hand side, or I guess my camera's flipped, so set low to be the far left-hand side and the high to be the far right-hand side. And because they're at the very ends of the array, we know that the elements that are there, they're just empty sets. And so it doesn't make sense to say that X is in those sets. And so we know that our proposition is true. If there's nothing in the low end and nothing in the high end, then X is definitely not in there. But if low is the very start of the array and high is the very start of the array, yes, we are still within our array bounds, and low is smaller than high. So our invariant starts off true, which is the very minimum requirement. Now we have our loop, as per the informal description of binary search. So while low is less than high, so while there is still part of the array to search, if we know our next line is to reassert our prior invariant, which we know is true because we haven't changed anything yet, we're still in the array, and we also have the guard condition is true. So we know if we're at this point in the loop, then low is definitely lower than high, or else we wouldn't still be in the loop. Now find the midpoint between low and high. This is low and high on 2, and here we're purposefully going to do integer division. This is because you go to like the, say there are 5 elements in the array, you can't go like to the 2.5 array element in the array. Junyi asks, what does assert here mean? Why P? Recall from last lecture that assertions are a way of saying that something is true. The program fails if the assert statement fails, and it's our way of making an argument. Where we have an assert statement, we are essentially saying, I can prove to you very simply, and you'd agree with me, that the following statement is true. What is P in this case? P is this invariant that we described on the prior page. It's just some logical statement that we're arguing is true at this point in the program. Junyi, if you have a follow-up question, feel free to put it in as well. So let's argue that P is still true and low is less than high. We know that this is true. There's no way anything could have changed. Now we find the midpoint, as I was saying, and we don't do with floating point division, we don't use doubles because it makes no sense to select the 2.5 element of the array. Now that we've done this, we have an additional thing that we can argue is true. We know that M must be bigger than or equal to low and less than high. How do we know this? Well, we had the equation on the last step, and there's no way for us to have defined M that way and for it to be outside the bounds. It's obviously between low and high, or at least bigger than low. Okay, makes sense so far, doesn't seem too bad. Let's continue within the loop. We have 3 branches within the loop. Our first branch, let's look at the midpoint that we just selected. Let's look at this element, and the way we look at that is with this syntax. A braces M is the element we're looking for less than the midpoint. This is going to be searching the left-hand side. I have to keep remembering that my camera got flipped. Is the element in the smaller side? If the element is in the smaller side, then we know that our original proposition is true. We're still in the array. We still haven't found the thing. And we can also say that we know for sure that X is in the left-hand side. Then what we do is we change our upper bound to be the midpoint. The upper bound is saying we know that it is not in that upper half. I keep using the wrong hand. We know it's not in that upper half. Julie asked, what does this notation mean? A, M, ... n minus 1. That's saying all the elements from the mth element to the n minus 1th element. And m was our midpoint, and n minus 1 is the end of the array. And so we're saying that x is not in that side of the array. And there probably should be... Yeah, and x is less than all of those elements. because the value of x is lower than those elements, we know the array is sorted and x was smaller than a of m. We know that x is also smaller than a of m plus 1 and a of m plus 2 and a of m plus 3, etc., etc. This gives us a guarantee that we can just ignore that half of the array. You know what? So that I don't confuse myself anymore, I'm going to see if I can flip the wrong thing. I'm going to see if I can flip my camera. Give me half a second to try do that. I have to find the right axis on which to flip myself. There we go. Okay, now when I point, it'll probably point in the right direction, which will be far less confusing for all of us. Okay, so we've eliminated the bigger side of the array, and now we can just focus on the smaller side of the array. What happens if x is larger than the midpoint? So this means everything on the left-hand side. So let's argue again. We're still in the array. We still haven't found the element. And we know for sure that x is bigger than all the things on the left-hand side of the array. Why? Because our array is sorted, and we know that it's bigger than the thing in the middle. So if it's bigger than the thing in the middle, it must be bigger than the thing that's a little smaller than the thing in the middle. And it must be bigger than the thing that's smaller than that, etc., all the way to the beginning. So low, which is marking out the side of the array that we know it's not in on the left-hand side, we say that it's at least the midpoint. We know that the thing we're looking for must be at least one more than the midpoint, because otherwise x wouldn't have been bigger than the midpoint. And we make our base assertion again. We can still argue, yes, we're still in the array, and we know that the thing we're looking for isn't in the side we just eliminated. That's what P is essentially saying. We're still going, and where all our values for our array indices are correct, but also the things that we've eliminated are not the thing we were looking for. Why do we need m plus 1? The reason is we're already looking at the mth element, and we want to say that everything to the left-hand side of the mth element including the mth element, is not the one we were looking for. And because we just looked at that one, because we were just looking at the midpoint and the midpoint wasn't what we were looking for, we know the value we're looking for must be at least one further on. So we're doing plus 1 there. Finally, we have our third branch. What if it's not in the left half and it's not in the right half? Well, we only have, assuming we know that the element is actually in the array, there's only one conclusion. If it's not to the left and it's not to the right and it's there, we must actually be looking at the thing right now. And so there's our proof that it returns. If the loop exits and it hasn't found the element, well, then we know that the guard is now false. Remember, the loop only ends when this guard is false. So when low is bigger than or equal to high, our loop ends. So our loop is bigger than or equal to high, which we have in our assertion here. However, we also have our proposition P, which says that low is less than or equal to high. So if low is less than or equal to high and low is bigger than or equal to high, there's only one possible value. Low must be equal to high. If low is equal to high, if that's correct, Junyi. There's no way for low to be bigger than high at the end of the day. So if we're in this condition, we're now at the point where low and high have converged. And remember, low and high, we're eliminating items on the left and eliminating items on the right. So if we have eliminated all the elements on both sides and there's nothing left, well, we know that x wasn't really in the array in the first place. So we return not found. And that is the formal proof of binary search. The only other thing we need to do is prove that at some point the loop actually does end, because if the loop never ends, we may not get to our condition. How do we know the loop ends? Well, this is just an argument that each time either high becomes, either we get closer to eliminating more items from the top, or we get closer to eliminating more items from the bottom, or we return. So in each one of these conditions, the loop is going to end, and we know that at least one of these branches is going to execute, and so we know that the convergence is going to happen, and because high is getting smaller and low is getting bigger, they must eventually meet, or will end through the early termination branch. Okay, any questions on that before we move on a little? I'll give you a few seconds to write something in chat or yell out if there's something that was a little confusing there. So moving on, up on screen now, we have the full code for binary search. And you can see it's not actually that long. Once I remove all the assertions, the code is only like 10-ish lines. Junyi, oh, we do have a question. Junyi asks, what's the difference between the assertion and the if loop? The reason we have the assertions is just for, it's not necessarily going to be in the code itself. It's there for us to make arguments and proofs. You can put it in the code, and then the assertions will detect if you actually have a bug and you've made a mistake, because the assertions are checking for things which you know must be true. So it's both for your thinking process and sometimes for your testing process. You can test if your thinking process has gone correctly if you put these in your code. If the assertion gets violated and your program complains, you know something has gone wrong either with your programming or with the design of your algorithm. So even though you can make your code a lot shorter, at the end of the day, the assertions aren't increasing the complexity of your code, and so are actually a good idea to even include when you're doing real programming, if you're trying to develop an algorithm or trying to implement a complex algorithm, as they will help assure you that your program is working the way you expect. We have another question. If there are repeated values in the array, will it find the position of the first one or just any one of them? That is correct. This version of binary search that we have written does not detect all the duplicate values. It finds the first one that follows this pattern. Again, figuring out exactly where that element is going to be is beyond what I have time to go through in lecture. But as you'll see when we eventually get to the exercises for you at home, this is one of the exercises, is to build a version of binary search that finds all the values, all of that value, and returns them, and to analyze it both for correctness and for efficiency. So here is something, a little bit of a story from John Bentley, who is a well-known writer on programming. And the story goes as follows. There'll be two stories. And forgive me for reading this off of the screen as I don't have it memorized. So John says, I've assigned binary search in courses at Bell Labs and IBM. Professional programmers took a couple of hours to convert the description that we just gave into a program in any language of their choice. Even pseudocode was fine. At the end of the specified time, almost all the programmers said that they had it done correctly. Then, John and his programming tutors would examine the code for about 30 minutes for correctness. After which, the programmers would then implement some test cases and see whether the binary search that they implemented was actually correct. Could they go from the high-level description of, okay, let's do this halving process and look for the thing in the right half? Did they get it correct? In several classes, and with over 100 programmers, the results varied little. And remember, these were professional programmers. 90% of the programmers found bugs in their programs. And John wasn't even convinced of the correctness of the code which found the bugs. John was amazed. Given ample time, only about 10% of the professional programmers were able to get this very small program right. They aren't the only ones, however, to find the task difficult. In Donald Knuth's book, The Art of Programming, in the history section, Donald Knuth points out that while the first binary search was published in 1946, the first version that was published that didn't have any bugs in it did not appear until 1962. And I actually have some personal experience with this. Let me bring... This is Matt Blaze, and he was one of my dissertation advisors who I worked with on research. In one of the first months of my PhD, he gave me a pen, and gave all my lab mates a pen, and said, go over to the whiteboard and write me binary search. Not a single one of us, all PhD candidates at a strong university, were able to write a correct binary search. Why? Well, one thing that all of us were missing was this idea of using assertions to prove the correctness of our programs. It actually turns out that by using this assertion structure, as a student was asking about earlier, you can come away with a much stronger guarantee that your program is correct. And I bet you that most of that 90% of programmers in John Bentley's group who didn't program binary search correctly weren't using any proof techniques whatsoever to assure the correctness of their code. Now, Matt is quite a funny guy.
And by the way, is there a more 90s series of words than a hacker named Matt Blaze? It's got to be right up there with Talk to the Hand, Furby, and Grammy Award winners Milli Vanilli.
And I highly encourage you to go find out a bit more about him as an interesting figure in the history of computer science as well. He is well known for breaking the security on government encryption that the US government wanted to roll out in all encrypted telephones around the country so that they could read what was going on. Okay, now we're ready to finally look at a bit of code. I know it's been a whole lecture since we've seen NEC code, but it's finally time for us to get back there. And here is binary search. And let me make it a bit bigger because I can see the stream could do with a size up. That looks decent. Okay, here's the program. We'll give it a run momentarily. First up, we're filling an array with all the odd values. So 2i plus 1 is an equation that generates odd values, and we're going to build an array of size 100. And then we have our binary search code over here. We'll ignore the main function for the minute, that's the driver. And you zoom out by one click so that you can see how short it is. This is all the code for binary search. It looks pretty simple, but almost every programmer makes a mistake. And if you were writing this in a really important setting, you would probably want to add some assertions in to test the correctness of this code. So let's go through it again. If low is bigger than or equal to high, which means we've eliminated everything from the left-hand side and we've eliminated everything on the right-hand side, and the two sides have come together, return the item not found. Get the mid. Figure out, is the thing that we're looking for, which we'll call the key, is the thing that we're looking for bigger than or smaller than the midpoint? And we're going to use this function CMP, which is written up the top. How is CMP defined? It is the value contained within the first pointer minus the value contained within the second pointer, and just compares the two. So it will be 0 if they're equal. It will be positive if the first item is bigger than the second, and negative if the second is bigger than the first. So that gives us our two branches here. Oh. So either we are going to eliminate things from the top and search the lower things, or we can eliminate things from the bottom and search the top half. And we know that if we're in the third branch, that we have actually found the item we're looking for. And that's it, along with a bit of driver code over here just so that we can test it. And this is just testing it for different values of the thing that we're looking for. And now we're ready to give it a run. I printed out for you what's in the array just so you can see. It's our beautiful odd numbers, 1, 3, 5, 7, 9, etc., etc. And then we'll look for all the numbers between 0 and 5 in the array. 0 is obviously not in it, 1 is in it, 2 is not in it, 3 is in it, etc., etc. And you can also do it with larger numbers and returns the value you expect. The odd numbers are there, the even numbers are not. So binary search is deceivingly both easy and complex. It's a short bit of code, but that is difficult to get right and also requires a little thought to analyze. Ooh, wrong thing. So this is great, but it assumes that we already have a sorted array. And that might be an unreasonable assumption if we don't know any good algorithms to sort the array. Well, we saw one earlier in this class, Insertion Sort. But Insertion Sort didn't have great runtime. How long was the runtime of Insertion Sort? Remember, the procedure was to pick an element and go through and compare it with every other element and put it in its right place. Pick the next element, go through every other element and put it in its right place, etc., etc. So give me a second to launch the Slido because I forgot to set it up properly. Take me a second to advance the next question. In the meantime, you can formulate your response. Yes, we did have a sorting function. That's Insertion Sort. Here we go. And we're looking for the average case. And I will correct that slight typo. So what is the average case runtime of Insertion Sort? Remember, the procedure is to look at an element, look through all the other elements, and put it in its right place. Pick the next one up, look through everything, put it in its right place. Look through an element, put it in the right place. And the majority of you were correct. It is n squared because for each element in the array, you've got to look through all the other elements on the other side in order to figure out where it should go. And repeating this process leads us to an n squared runtime. So, not particularly good. Quadratic, that means it's going to grow really quickly as the number of elements in our array grows. And very soon, if we're trying to sort like an array with billion objects, that's going to become untenable. But you might ask me, Shannon, when am I ever going to need to sort a billion elements? Like, have things. Well, one way to think about it is imagine you are Facebook. and you have all the messages that a particular user is sending on WhatsApp or the same thing with WeChat. You have a bunch of users who are sending a bunch of text messages. How many of you have sent one text message this morning? Probably a lot of you. No, I certainly have. How many of you have sent out like 30 text messages? I mean, I probably still have sent out 30 text messages, just even in the Zoom chat I have. And the interesting thing about these messages is when you load up your computer, the server that stores all the messages, or when you load up your phone, has to figure out which of the messages arrived in which time and how to show them to you. Particularly if you then start searching through them and want to find old messages, it needs to have some way of keeping track in its giant database of which messages should appear when. Now, a billion items is going to be very difficult to sort with n squared because a billion by a billion gets very giant very quick. So we're going to need a better sorting algorithm, and this is what we're going to focus on for the majority of the rest of our time together. Oh. And this is quicksort, an algorithm designed by Tony Hoare. Yeah, we can do better than n squared. I've got these few slides. Quicksort is well known as being one of the fastest practical sorting algorithms. So there are a few other algorithms which come close in theoretical complexity, but quicksort in the real world ends up doing fantastically most of the time. Quicksort is one of the more complicated algorithms that we're going to learn in class, and so we're going to take nearly a full lecture to go through it. Here's the general idea. Just like with binary search, we're going to divide up our arrays into different regions. Except instead of already having sorted regions, some of our regions are going to be sorted and some of our regions are unsorted. Just like in binary search, where we pick some element as the focus, in binary search we picked the middle element, we're going to pick an element to be the focus in quicksort as well, and we will call this element the pivot. And the reason why we call it the pivot might become a little clearer a bit later. The key rule in quicksort, the thing that makes it all work, is that after we're done with each round of the algorithm, everything to the left of the pivot should be smaller, and everything to the right of the pivot should be bigger. Now, when we do this the first time, we're going to have the middle part where the pivot is, and anything equal to the pivot should be right next to it. But in the zone to the left, we'll still have unsorted stuff, but we know it's smaller unsorted stuff. And to the right, we'll have unsorted stuff, but it will be bigger sorted stuff. And maybe the gears are starting to turn in your mind. Well, what would happen if I now went to the unsorted stuff and I did the same thing? I go to the unsorted stuff and I choose an element to focus on, and I put all the smaller things to the left, all the things that are the same in the middle, and all the bigger things to the right. And now I do this again, and I keep doing it and doing it and doing it. And pretty soon, these regions are going to get smaller and smaller, the ones that are all lumpy, until they all smooth out, just like you see in these different figures here. In our first figure, I'm not sure where figure A disappeared to. Oh, figure A would have just been all lumpy, all everywhere. So in figure B, we've chosen the middle area as, we've chosen an element as our focus. We put everything to the left of it, and then everything to the right of it. Everything to the left of it that's smaller, and everything to the right of it that is bigger. Then we have our two unsorted sections. We do our recursive calls on each of those and do the same thing to make them less lumpy. And then finally we end up with our sorted version and we are all happy. So this is the high-level description of it, and we'll get into some of the details now, which admittedly this might take you a few tries. Don't worry about not getting it right away. It is definitely one of the more complex algorithms that we'll learn in this class. So here I've drawn out earlier, and I might have to hide my video at various points, because I think my scribbling got a little too close to the bottom of the screen at points. But here's some scribbles I did earlier of a sample array. This is just a set of numbers that I've randomly chosen to demonstrate, and it's unsorted, and we want to make it sorted using quicksort. Our first step is to choose an element as our pivot, as the element we're going to focus on. In the demo with the scribbles, we're going to always choose the first element of the region as our pivot. Once we've chosen the pivot, we go through the array and find all the things that are smaller, all the things that are bigger, and all the things that are the same. And remember, our goal is to put all the smaller things on the left-hand side, all the things that are the same in the middle, and all the things that are bigger on the right. So I've gone through the array, and I have done this one by one. And don't worry for the minute exactly what the C code will look like to do this, but it's the same kind of thing you know how to do. So as you go through the array, is this number bigger or smaller? If it's smaller, put it in on this side. If it's the same, save it for the middle. And if it's bigger, start it at the other end of the array. And exactly how this works with swapping, etc., can get a little hairy. You can, of course, do it by creating a new array of the right size, but the process itself is going to be a little tricky, so we'll save that for the minute. Now we have exactly what we described earlier. The things that are the same in the middle, the things that are smaller on the left, and the things that are bigger on the right. Now let's drill down on one of the unsorted areas. Let's say the smaller unsorted area on the left. So all the numbers that are smaller. Well, let's just focus on those, and we'll pick our pivot again as the first element. We'll do our procedure where we find all the things that are bigger and all the things that are smaller, and we arrange them. Things that are smaller to the left, things that are the same in the middle, things that are bigger to the right. And now we have 3 areas that might be unsorted. Yes, it is exactly what you do is you compare the pivot with all of the others in turn. The tricky part is not understanding that you have to compare it. It's understanding that how exactly you fit them into the array when you're actually doing the programming is a little tricky. But you're totally right that you do as you go along with each of these elements is compare them to the pivot. I'm sorry if that wasn't clear earlier. So now we have our 3 areas again. The area that's smaller, the area that's the same, and the area that's bigger. Only now all of our areas are only one element in size. And if an array is only one element in size, well, it's sorted. It's sorted with itself. And the middle element, we know the middle element is always in the right place because all the things on the left are smaller and all the things on the right are bigger, so it's in the right place. And in this case, our bigger element is also only one, so it's sorted too. Great. Now we know we've sorted all the things on the left, sorted all the smaller things. The middle region is good because that's how we designed our algorithm. And we have our region on the right, which is all the bigger things, and it's still unsorted. Well, we now know how to tackle this, so let's go ahead and do it. We'll pick the first element as the pivot. Compare each of the elements in turn. Is 27 smaller than 74? Yes, it's going to go on the left. Is 38 smaller than 74? Yes, it goes on the left. Is 89 smaller than 74? No, it's bigger, it goes on the right. And there is our construction. 27 was smaller, 38 was smaller, 74 is our pivot in the middle, and 89 is larger, so it goes on the other side. Well, now we have the left-hand side to sort again. Well, out of 27 and 38, we'll pick 27 is the pivot, and then 38 is larger, so it goes on the right-hand side. And we have a pivot and a single sorted element. We know we're done. Both of those are sorted. We will get to the real code, don't worry. I hear you. We are just for the moment trying to understand how it works so that eventually we can understand the real code. Without having it visualized like this, it's much harder to understand what the code is doing. So returning to our example, 27 and 38 are now sorted in our recursive stack. The pivot in the middle, we know it's in the right place. And on the right-hand side, we only have a single element, so that's sorted as well. So we just sorted the left-hand side, we just sorted the right-hand side, we have our pivot in the middle, and now our whole process is complete, and the quick sort procedure terminates. So we have two recursive calls, one to the left and one to the right. And importantly, we also have this partition function. This function is going to be the one that actually does this comparison and does this creating of the ordering. And that's how quicksort goes. Find your pivot, partition around it, things smaller on the left, things bigger on the right, and then rinse and repeat with both sides. That's it. Simple. So now we're going to go to the formal description of quicksort and try and prove it's correct, while also hopefully getting a bit of a more understanding of how it's working. And we may not even finish the correctness proof today. We'll see how we go. As always, we're going to construct an invariant. Remember, the invariant is a statement that we use just to help our thinking and to argue things that we know are correct in order to prove that overall our program is correct. Our invariant this time is getting a little complicated, but if we break it down into parts, it's easier to understand. So the first is we're going to have some variables fe and fg, which will mark positions in the array. And the first line says, yes, they're just positions in the array. They're between 0 and n, where n is the length of the array. Second condition, let's say we have some element p. Everything between 0 and fe minus 1, so maybe this will be our left-hand side, is smaller than p. Between fe and fg are going to be all the elements that are equal to p. And between fg and the end of the array are all the things that are bigger than p. So in plain English, with each of the parts of it, both sides of the pivot are in the array. So fe and fg are in the array. Everything on the left of the pivot is smaller, everything in the middle is equal, and everything on the right is bigger. And this is just a formalized way of saying it by using two variables, fe and fg, to mark out where the partitions start and end. This is what the quicksort function looks like in our description. We need a base case. It's a recursive function, and so if we don't have a way to know when to not recurse anymore, it'll just keep going infinitely. Our base case here, if you only have one element, the element is sorted, you can just return. Why is my clicker not clicking? Otherwise, if you have more than one element, first thing, choose a pivot. Right now, we're going to choose the first element of the array as a pivot, but this same procedure will work no matter which element you choose. And as we'll discuss tomorrow, the choice of pivot is actually going to be really important. Then, assert that there's at least more than one element, and we know there's more than one element because otherwise we would have gone into our base case. So there's more than one element, and we know that the pivot is one of the elements in the array. How do we know? Well, we just chose it to be the first element, so obviously that's in the array. Great. Now we have our partition function. This was the function that we're defining to divide things up into the three different areas. And we'll check our assertion again. So our assertion, everything on the left is smaller, everything in the middle is equal, everything on the right is bigger. And assuming that we use this assertion, to build our partition function as well, we know that it's true. That's exactly what our partition does, is preserve this condition. Then we recurse on the smaller side, we recurse on the bigger side, and now we have another assertion. We know that after calling quicksort on the left-hand side, if quicksort works, everything on the left will be sorted. We know that if quicksort works, everything on the right will be sorted. And we know that from our assertion that the things in the middle are bigger than the things on the smaller side, and they're smaller than things on the bigger side. With these three things, we've covered the entire array, and so we know for sure that the whole array is sorted, because if the things on the left are sorted, the things in the middle are in the right place, and the things on the right are sorted, well, there's nothing else. We've sorted everything. Now we just have to define the partition function in a way that makes sense. So again, what the partition function does is it takes the elements of A and puts them in a smaller region, an equal region, and a bigger region in relation to some pivot that we've chosen. The function is going to return the boundaries of the partition. So where do each of these areas start and end in the array? Notice that I've used the word permute here. This means that it's just going to shuffle the entries in the original array to their correct places. This is not actually necessary for the partition function to work or our proof to work. You could create a new array and put the order there, but with the permutation definition, we're going to be a little more efficient because we're not going to have as much memory that we'll use up as if we're creating a whole new copy of everything. In order to prove the correct partition function, we'll need another invariant. Let's call this one P, and it's pretty similar except with the addition of this next variable, and we'll see what the next variable is momentarily. So as before, all of our variables are mark-out regions in the array. Everything on the left side is small, everything on the middle side is the same, and everything on the right side is bigger in relation to our pivot element P. How does partition work? Okay, let's initialize all our variables. Let's start off with next and FE both marking the far small side of the array. They're all far on the left-hand side. FG marks the end of the array on the other side, and let's assert P. P is true because let me go back. P is true because the regions that I've marked out show that there are no elements on either side, and so they must be true. For our partition function, we're going to keep looping until we get to the end of the array. While next is less than FG, which is going to mark the end area. Then we're going to assert that our proposition is still true. We're still in the array, all our ordering still works, and we'll check our loop condition as well. Remember, this is just for the sake of argument. We obviously know that next is less than FG, otherwise we wouldn't be in the array, but we're doing it here again. Now, if the element we're currently looking at is less than our pivot element, swap the element that marks the swap the two elements, swap the element we're looking at, A next, with the element that marks the beginning of the array. Because we know that the beginning of the array is the place where we put all the small things. So put the small thing at the very start of the array where it should be, and just swap it with the current one you're looking at. Then move the boundary of the small area up one, because we know it should now have one element in it, and also move on to look at the next element. In the beginning, P equals A of FE. You can choose whichever pivot element you like. You're right, I did omit the definition here. The way we're choosing pivot elements for the moment is we are choosing the first element of the array. And we will go through this next branch, and then we'll cut off for today and leave us with one lecture to go. So if the element was smaller than the pivot, put it at the very beginning of the array, and then say the region that contains small things now has one element in it. So we're incrementing FE by 1. On the other hand, if the element that we're looking at is larger than the pivot, Well, we should put it at the end of the array. So put it at fg minus 1. Remember, because our array starts at 0, if we were to put it at index n, that would be outside. So we put it at n minus 1. And then we say, well, the place where the big things begin is no longer at the very, very end. It's got one element in it. So we move it over 1. And then we assert p, and we keep moving onwards. As you can see, we have another loop condition to go. We'll cover that tomorrow along with a bit of a recap of these former loop conditions. And that's it for quicksort. Then we're going to go to our efficiency calculations. We'll have a brief discussion of some more algorithmic ways to think about things. We're going to revisit the Fibonacci sequence for the final time and then close on that with a few words from me before you're done with me for the semester. However, given that the assignment is still running, I'm going to be around for consultation hours even over the next few weeks for you until the assignment ends. And even then, you might still see me a little bit. Don't worry, I'm not going too far. You'll be in good hands. And thank you very much, and I will see you tomorrow. Oh Lord, ternary search. We are not doing ternary search today. Any other questions other than that? If you wanted to learn about ternary search, either come to office hours or post a question on Piazza. Yeah, the mid-semester test solutions will be out shortly. I just have to make a video explaining them. And if you want to discuss the mid-semester, if you just want to discuss it and not ask about a regrade, you can email me and we can set up a time, or you can find a time with your tutor. And if you want to do a regrade request, well, there's a special online form that we put in the announcements for that, and then they'll all be processed in order. The marking for the mid-semester test is finished except for a few special cases. If you're a special case, you should get an email from Janjong soon. In theory, it wouldn't make sense. Daria asks, in theory, it wouldn't make sense to sort an array just to find an element in it because no sort algorithm has a better average case than O of n, linear search, right? Yeah, that's correct. If you're only looking for one element one time, then you wouldn't sort it because you're at best do n log n, average case, and you could do just log n with a binary search. You could just do it with O of n linear search, and so it wouldn't be worthwhile sorting it. However, in most cases, when you're looking for something using programming, it's going to be a repeated operation. So often it does make sense to sort it. It'll come down at the end of the day to the specifics of the problem you're looking at. Okay, thank you very much, everyone.